online.
Greetings, everyone. My name is Hernani Nascimento from the Meteorology Program of the Federal University of Santa Maria in Brazil, and would like to welcome everyone to the 5th presentation of the webinar series, Nowcasting Operations and Techniques, Perspectives for South America. This series is supported by the Nowcasting and Mesoscale Research Working Group of the World Weather Research Program of WMO, and we'd like to thank all the individuals who have registered in today's talk. The series consists of webinars that are broadcasted live, always at 18 UTC on the first Friday of each month. The presentations are also recorded and made publicly available in the YouTube channel of the Department of Atmospheric Sciences of the University of São Paulo. For these webinars, a number of professionals with long experience in research and operations in nowcasting of convective storms have been carefully selected to give talks. Today's guest speaker is Rita Roberts from the USA. Rita's talk will be followed by a Q&A session. And for that, we'd like to ask the audience to place your questions in the Google Meet or YouTube chat. We will read your questions right after the presentation. And please, for those in the Google Meet session, remember to keep your microphone muted. Now, I'd like to pass the words to Rachel Albrecht, who is co-chairing this webinar presentation with me, and who will introduce today's guest speaker. So Rachel, please, the microphone is yours. Thanks.
Hello, everyone. Rita is a researcher scientist from the National Center of Atmospheric Research in Boulder, Colorado. And she has been working there as scientist and project manager for the past 38 years, and recently retired last year, right? She has been one of the scientific leaders for NCAR Research Applications Laboratory, working on convective weather and nowcasting group, and has participated in 16 national and international field campaigns. She used observations, including radar, satellite, to examine the initiation, evolution of convective storms and the hazardous weather such as microbursts, non-supercell tornadoes, and flash floods. I had the pleasure of working with Rita at WMO Nowcasting Working Group, where she was co-chair of that group and led the Lake Victoria High Impact Weather and Lake System, or HIGHWAY, as we for short, field campaign that was placed in East Africa over the Lake Victoria Basin, which is the subject of her talk today. So Rita, thank you very much for agreeing to give us a little bit of the results and outcomes of HIGHWAY.
Thank you, Rachel. It's my pleasure to be able to talk with you all today and share what I think is really a fascinating project that was held in East Africa. So many thanks for including me in these webinars. So I want to talk about the outcomes from HIGHWAY and also some of the implications for really developing a sustainable nowcasting and early warning system in that area of East Africa. So the map on this slide shows Lake Victoria Basin in the darker green shade. You can see that it's bounded by Uganda, Kenya, Tanzania, and Rwanda and Burundi all have responsibility for the forecasts over the lake and any warnings that are produced. This lake is the second largest in the world freshwater lake, but it is Africa's largest freshwater lake. It produces 1 million metric tons of fish annually. It provides the livelihood for 5.4 million people around its shoreline. Approximately 217,000 fishermen go out on it daily or at night. The claims, this lake claims approximately 1,000 lives each year due to drowning. So it's a very challenging, interesting area. This figure shows the terrain of the region. You see the lake in the center. The equator actually rides across the northern part of the lake. And there's the Kenyan highlands and the Ethiopian mountains to the east and northeast. And you've got a mountain range that runs through Rwanda and Congo on the west side. And so the terrain's very complex and makes the weather also very challenging in this area. Okay, this is one of Rachel's slides. She looked at 16 years of high resolution lightning data. The top panel shows a climatology of the lightning. And so this region of the world, this has the second highest flash rate density or frequency of lightning occurrence in the world. The highest from her study is this Lake Maracaibo. Sorry if I mispronounced that. That's in Venezuela. So lightning is really an issue in the area of the lake. Also, water spouts occur. We're not sure how frequently they occur on the lake, but they do occur. And in fact, if you look at this article on the left-hand side, you'll see that they were writing about these water spouts over 100 years ago, trying to figure out how they formed and what their composition was, what the funnel looked like, etc. And these two photographs on the right are from Uganda region. The one at the bottom from Busi Island, there was some fatalities associated with this water spout. So they can be dangerous. That was danger on the island, but it can be dangerous for fishermen on the lake as well. There are a lot of hazards that have been cited over Lake Victoria. This is based on a lot of surveys that were collected by Fred Samazi in 2010 and 2011. These include really strong winds, rough waves on the lake, severe thunderstorms, heavy rain, fog, and water spouts. So there's a lot of weather that can impact those that use transport on the lake. Boats do capsize on the lake during severe weather, and this is one of the main reasons of the number of fatalities that occur on the lake. This is due to strong winds and rough waves. But boats also capsize due to overloading, and this can be yet another reason for the drownings on the lake. Historically, it was felt that there was up to 3,000 to 5,000 fatalities occurring each year. If you asked any country that borders a lake, this is the number that they would quote. Of course, there wasn't any analysis done at all to verify that. But the problem was realized that severe weather was causing problems for the fishermen on the lake and the people who need transport from the islands to the shore, and any users of the lake. This is a problem. So the Met Service, actually all of the national meteorological services that support the lake, approached the WMO and said, we need help. We need to figure out, we need to understand the storms better over the lake, and we need to be able to provide better forecasts for the users of the lake. So out of that request for help came the HIGHWAY project, which is the High Impact Weather Lake System. This was a 3.5-year project that ran from 2017 until last year. It was centered on Lake Victoria Basin, of course, in East Africa. It was funded by the UK Foreign Commonwealth Development Office, and it was led by the WMO. So there were 4 primary goals of HIGHWAY. One was to collect enhanced observations in the region so that we could better understand the convective storm development and evolution and severity over the lake. The other Another goal was to develop nowcast and forecast products for an early warning system. There essentially was no early warning system in the area prior to HIGHWAY. The third goal is to improve fishermen, farmers, and transporters' understanding of the weather forecasts and warning. This is a big deal to try to make sure that they understood the information they were getting. And finally, to conduct a socioeconomics benefit study for a sustainable early warning system in the region. Okay, so I'm going to talk a little bit about the observations that we obtained and during HIGHWAY, and we essentially ran a field campaign, not your typical field campaign by any means, but it ran from 1 March through to the end of December. And it covered 2 rainy seasons from March to May and October to December, and the relatively dry season from July to August. And this map shows the observations and the ground instrumentation that we were able to gain access to. I want you to keep in mind this was challenging because each country typically was not willing to share data with any other country, and they have many protocols and restrictions. So the field campaign made it possible, because we were all partners in this project, to get some of this data and archive it. And so we had a S-band radar at Mwanza. This is Tanzania radar. There was a Rwanda radar, a C-band in Kigali, and then there was a radar that was installed later in the field campaign in Entebbe in Uganda, on the north shore of the lake. But we didn't actually get any data from Entebbe until 2020. So no data to be able to mosaic together with Mwanza. You see upper air stations, those are in orange. I'll talk more about that in a minute. There was automatic weather stations from each of the countries, their own synoptic reporting stations. But you can see in this map, we had access to very few of those. We relied on getting that data from the GTS, the WMO GTS system, and there just weren't that many that were reporting. The TOMO stations that you see here in magenta, that's a commercial network of stations. They provided data for free during the field campaign, which was really great. And 3D printer automatic weather stations that were mainly supported by Globe and located in Kenya, and some were installed in Uganda, and then MODES receivers. But the big disappointment, of course, is that there are no buoys that were available on the lake. None of the countries had any that were working anymore. And so that's of course a real disappointment. Okay, so a big effort during HIGHWAY was really to rehabilitate the surface stations and the upper sounding stations. You can see in this map on the left and the red dots on the map, these are where the upper air stations have been located for several years, but they haven't been working. There haven't been soundings released from any of these for the last few years prior to HIGHWAY. So that's a real issue. If you want to run a numerical model over the region, you have no soundings that you can use to initialize the model, and very few surface stations reporting to the GTS that you can initialize the forecast model. So work was done, especially by WMO, to work with each country to get their upper air stations fixed and running. And by mid-August, Kenya had their Nairobi and Lodwar sites operating, and they were collecting 2 soundings per day. But by the end of middle of 2020, in the end of the field campaign, they essentially ran out of consumables, like the balloons and the instruments. In Tabi at Kampala, there was that upper station was refurbished and was working, but we could never access the data. And then the Dar es Salaam station never received their hydrogen generator system that they needed. And so there were no launches from that site during the field campaign. So this is a challenge. This is a definite challenge when you're in developing countries of being able to have the radiosonde data you need to initialize numerical weather prediction models. It's not just that you need the station working, but you need to have a ready supply of consumables always on hand. The data needs to be transmitted to the GTS. And ideally, you want each site to launch 2 soundings per day. So you can view these as either challenges or opportunities, but clearly for these countries that bound the lake, they need to earmark funding to continue to support their upper air stations and the staffing for launching the radiosondes. These stations are really needed for understanding the environment over the region and potential severity in the region as well. During HIGHWAY, and actually during normal operations for the forecast offices in the region, they have access to the EUMETSAT satellite imagery, and they also had access to some of the satellite application facilities nowcasting products, one of which is shown here. This is the rapidly developing thunderstorm product. I'm not sure if it runs there in South America, but I know it does run in Europe and some other places, and essentially tracks the growth and decay of storms on the satellite imagery and their motion. So some of these products were made available, but I can't really say how many of the forecast offices actually looked at them. We also had access to the Earth Network's Global Lightning Network. This is another commercial entity. They provided this data to us for the project for the whole year of the field campaign. So this was really wonderful. And in fact, Katrina Wirtz and Steve Goodman have taken 7 years of this data and compiled a lightning climatology, which you can see in this 2-panel figure to the right, showing that the high occurrence of total lightning strokes tended to occur over the land. It did occur over the land during the day, but the maximum strokes occurred over the lake at night. So you can see the hazard this presents to the many fishermen who do go out at night to fish, having those severe thunderstorms forming overhead. Okay, so this Earth Network system is an incredible tool for the detection of thunderstorms. It has been very expensive for forecast offices in the region to pay for it. And so when they don't have the funding, they discontinue using it. But again, during HIGHWAY, it was for free. So as you saw in that first image I showed, there was radar data, and there were radars, particularly the Mwanza radar that was located on the southern shore of the lake. And this was really exciting to be able to go into this project where we didn't feel like there was any radars really operating routinely or any good data to find that there was indeed a radar that was and could be totally operational during the field campaign and provide really good quality data. So I'm just going to click on my little laser here and move it over to this upper left panel, just to explain a couple of things about the radar image if you're not familiar with radar data. First off, The coastline, the southern coastline of the lake is shown in white here. The red cross shows the location of the radar. We're looking at a reflectivity field that gives a sense of the intensity of the storms. And so you can see storms here that are running about 45 to 50 dBz in intensity all along this region over the lake. And another very interesting feature is this thin line that shows up in the clear air return over the lake. This is a feature that isn't normally seen over lakes. It's commonly seen over land. It's essentially the conversions associated with gust fronts or thunderstorm outflows. So a good marker of where there may be strong winds over the lake. So here, this upper left panel is a gust front. In the upper right panel, we see a land breeze located here that forms at night as the air flows off the land into the ocean. And on the lower left, we see gravity waves here, as indicated by the white arrows that can show up over the lake. And in this last panel, we see another nice boundary, but of unknown origin. We don't know where it's from or whether it's, well, it's not birds, but most likely insects in a combination. Anyway, the point is that this is not only great data for tracking the storms and understanding what the storms are doing, but now we can also track the gust fronts and the convergence boundaries. And we know that these are important things because of all the research we've done through the years. Convergence boundaries are able to initiate storms and favorable environments, and they also affect the evolution of the storms and certainly the near surface winds. So this is a movie loop from Mwanza radar. Oh, I'm sorry, from Entebbe radar. In the center of the screen, you can see where Entebbe is located, and that's the radar center location. This shows, it's probably slow moving on your side, but it shows a group of storms moving offshore onto the lake. They produce a very nice thin line or gust front that moves down through the lake. But as it loops through again, you'll also see that there also is a presence of a land breeze. And when the gust front and the land breeze collide, new convection occurs. I'm sorry, I don't think I can show the laser on this loop, but you can see the new storms that form in the lower left-hand side of this image, and they continue to just move on all the way down the lake, creating likely a lot of problems for whoever was out fishing that night. So radar is really a great tool for identifying strong winds, severe weather, for detecting them, for tracking them. And this is just another example using both the Mwanza radar data and the Entebbe radar data on the lower two panels to show you some severe weather examples that are occurring over the lake. On the upper left, we have a storm that's moved offshore from Mwanza, and it has very strong rainfall occurring in it, and it also has a gust front associated with it. And if we look at the corresponding, the corresponding velocity information, you can see really strong winds associated with this gust, behind this gust front, 25 meters per second, or in the US, that's about 50 knots. This is really strong winds to have near the surface on the water, and likely contributing to really strong wave heights. A different case from Entebbe. So the radar is located here along the north shoreline, and it's seeing storms to its southeast, located here. If we look at the velocity data, we see an interesting signature. We see velocities toward the radar of 7 meters per second and velocities away from the radar 17 meters per second. And essentially, this is a microburst downburst situation where you have a downdraft, very strong downdraft coming down to the water and spreading out radially in all directions. And this creates quite a wind shear in that very center region. It's a problem for fishermen on the lake. It's also a problem for aircraft that are either taking off or departing. And there is an airport located near the heavy radar. So radar is a great tool for seeing these things, these details. And so we've gone through all of the radar data that was collected during the field campaign, primarily the Mwanza radar data, and looked at where storms initiated, how they evolved, what type of severity was associated with them. As you can see in this squall line that develops, north-south squall line, that eventually moves to the western side of the lake. So I'm not going to go through all of these plots in any details, so you can breathe a sigh of relief. But this is just to show that after looking at all those days of total, when there was total radar coverage over the lake, that there are essentially 6 modes of convective storm evolution. Each column in this figure is one of the modes. So 4 are shown here. Essentially, there's a lot of initiation that occurs along the northeast coastline of the lake. Storms later develop and then move to the southern part of the lake. Or you can have storms that just form in the center of the lake and intensify. So there are different modes. And from these 6 evolution modes, we can kind of summarize the pattern of the weather that tends to occur over the lake. To start with, and we know this from the lightning data and also from satellite data and others, there's very minimal weather over the lake during the afternoon. Most of the weather is happening over the land, over the higher terrain, through warming and over lake breeze circulations that set up. However, as you go into the nighttime period, and this is nighttime before midnight, a lot of storm initiation occurs in this region of the lake. And then storms start to organize, maybe merge, and become more established convection. In the period from midnight on into early morning, most of the storms tend to be in this region of the lake. They're much more organized. There's upscale growth, and that's a real problem area for those, again, fishermen on the lake. And finally, in the morning, you have convection that's maybe moving off the lake and onto the land, but dissipating. But there's still some good organization and upscale growth also occurring in this area of the lake. There's some nice summary of this convective modes scenario that's been done by Ana del Moral Mendez. And I also want to refer to you that she's doing a seminar next Tuesday. And there's a link put here. I don't know if it would be possible for you to check in, but she will be showing a lot of detail of her research on the storms over the lake. I think you find it really interesting. Okay, so we that's the observations. There was also forecasts and Nowcast products that were being used during the project. Each forecast office in each of the countries surrounding the lake typically had access to global models, and an example is shown here for the UK Met Office Global Unified Model. So in their standard operating procedure, they look at these global models, and they also had other more regional forecast models that they might be looking at as well. And they're definitely looking at the satellite observations that were available to them and any surface observations that were coming into their office. But some of that data doesn't come in very routinely in some of the countries. For HIGHWAY, the UK Met Office ran an operational high-resolution 4.4 kilometer regional tropical Africa model. We call this the TA4 model, and it's a convection permitting version of the unified model. So they had this running. It was not always available for the forecasters in each of the countries to view, but they tried to get it on the web and make it available as much as possible. But you can see when you have the global model running, it's producing widespread precipitation in this general area around the lake, but nothing really convective. The TA4 model is placing a storm right near the lake. And then we have the NASA GPM Global Precipitation mission is showing precipitation there. So there is promise, of course, when you have the regional models running, that you can get a much more specific and precise forecast of convection over the lake. So one of the HIGHWAY objectives was to include lightning diagnostic in the TA4 model, and this was done. The comprehensive verification hasn't been done yet to compare if the location and timing of the model precipitation is similar to the lightning climatology. But that's a first step in the right direction towards including lightning data in the models. We also looked at how the model compared to the radar in when first convection occurred. So in this plot here, you see we have radar, the time of convection initiation from seen on the radar over the lake, and the time of convection initiation over the lake as seen by the model. And there's a fair amount of scatter in here, but you've got a 0.71 correlation in agreement that doesn't seem too bad. But really what's going on, if you look a little closer, is that convection initiation is actually occurring early in the day on the radar over the lake, or early in the afternoon. And the model is lagging behind seeing that convection by about 5 hours. However, as the day progresses into the evening, the agreement is actually a lot better. And so that's again encouraging that to get the timing of when convection is going to occur. We also compared where the model forecasts that first convection. And on the left here, you see the radar imagery for a particular case at this time. And this on the right is the TA precipitation forecast valid at this time. And it's clear that you can see that they don't line up in the same part of the lake. The model forecasts of precipitation location nearly always puts the precipitation too far to the west of where it actually occurred. And this won't be any surprise to most of you, because this happens with most models, that getting the location or the timing are the main challenges for the models to get convection correct. And then one other comparison was done by the Met Office. They compared the TA4 model to surface stations that were located along the lake to the surface stations that are shown here at Mwanza and Kisumu in Kenya. And it's pretty clear that you can see here, the blue is the forecasts and the red are the observations, that the TA4 model has a negative bias in the wind speeds for the sites shown here, and also the other sites that aren't shown. So that's a problem that needs to get improved so that you can get good wind speed estimates and forecasts for the lake. Okay, so I think I've kind of said that. Okay, so we also had Nowcast products. HIGHWAY only funded one specific Nowcast product, and that's what's shown in the lower two panels here in this figure. This is the Lagrangian nearcast model produced by Ralph Peterson and colleagues. And it essentially provides information using the severity data and model information to look for regions of destabilization in the atmosphere and where convective activity might occur later in the afternoon or in the evening. So this product was funded for HIGHWAY. We could very easily have run extrapolation techniques at the radar sites that had radar, at the radar sites, I'm sorry. We could have run extrapolation techniques on the radar data or on the Earth Network's lightning data, but none of this was funded, and it was an issue primarily because this information, both of these information, were not getting to the forecast office in real time for most of the offices in these different countries. So these are just what was available or could be done. And some of this could have been very easy if the data had been transmitted routinely and quickly to central forecast offices. So we conducted training workshops as part of HIGHWAY. It was clear for Mwanza, which provided most of the coverage over the lake, that data was available to view at the weather forecast offices as web images, but the actual gridded data was not making it to the central forecast offices where you would want to be able to render to the data and really inspect the data. And none of the forecasters really had any training on looking at the radar data. So in these training workshops, we had seminars, but we also ran modules that they essentially had to go in and forecast or nowcast what type of weather they expected in the next hour, how much precip, where they expected strong winds. And so the groups got together, and these were the challenges they faced to not just interpret the data, but be able to nowcast using the data. So this is shown on the right. These photos are from the Tanzania workshop, and the Uganda workshop, which was the following year, was held virtually because of COVID. So because we couldn't do some of this kind of classroom style training, we created these online radar materials, like a training module online, but also that included quizzes for the forecaster at the end of the module for them to see if they were correctly interpreting radar data. By the end of HIGHWAY, Tanzania was able to get their raw radar data transmitted to the central forecast office, and that was huge. And then by February of the next year, the Entebbe radar was being displayed in the central forecast offices there. There were several training efforts, and the training events held for forecasters on strictly forecasting using the models for the East African region as well. And that should continue. I mean, WMO has these regional training centers, and they could really use the data from HIGHWAY to continue training forecasters in other regions and new forecasters coming into the forecast offices. Okay, so HIGHWAY wanted to develop an impact-based early warning system. There was no really early warning system available in any of the countries. Fishermen, prior to HIGHWAY, they didn't trust the marine forecasts. And the main reason was because there was only one forecast put out once a day, and it was for the whole lake, and that's what Uganda put out. And the same was done by Kenya, and the same was done by Tanzania. And they may not have been the same forecasts. Who knows what models they were using. The fishermen, they didn't find the forecasts usable or actionable. And the need is to have really accurate predictions of wind speed and direction and severe weather. So as a result of these preliminary surveys done at the start of HIGHWAY, regional and national workshops were held with the forecast office, forecasters, stakeholders, government officials, the media, local intermediaries, and end users. They were all gathered together at local workshops and regional ones to come up with a plan for getting an early warning system in place. And this is a totally new direction for the weather services in Africa. And actually, it's a big effort in any country to try to change the information, the meteorological information, into something that's really pertinent and useful for the end user. Who doesn't know meteorology? Okay, so out of these workshops, it was agreed by all the countries that they would split the lake into 10 marine forecasting zones, and you can see which countries were responsible for the various zones. And then they produced this graphic forecast tool, which I just think is tremendous. It's issued for 12-hour forecasts and a 24-hour forecast. It provides information. If you look on the left here, information for Saturday morning, the afternoon, night before midnight, and night after midnight. And instead of seeing that you have wind strength of 10 meters per second, you see that the wind is blowing the trees very strongly. The trees are bending in the wind. All of these icons are meaningful to the fishermen. Instead of having, for example, wave heights that are 1 or 1.5 meters as the forecast, they can look at this and say, oh, if I have small waves, maybe I don't need to be concerned if the small waves relative to my body come mid-height. However, if the height of the wave comes up to, the height of the man, then there's much more of a threat to the fisherman if he decides to go out on the lake. In this particular case, a warning is issued for fishermen that they should think very carefully and prepare if they're going to go out on the lake that morning to fish. So I think this is really exciting because this is what the fishermen are seeing or hearing about. And so we talk a lot at the WMO and in the world about the challenge of doing research to operations. Well, this is not only research to operations, this is a terrific example of transferring from operations to the end user. And that's, as you know, a great challenge. Okay, the forecasts are being disseminated by local and regional radio broadcasters who they've been trained to interpret the forecasts. They're shared in the native languages of the Lake Victoria community. The forecasts are broadcast at fixed time, and those business entrepreneurs around the lake, they take them really seriously. Another method of dissemination that occurred during HIGHWAY was to share the forecasts with the WhatsApp group, and this was terrific, because it was free for the fishermen and the local community who had WhatsApp on their phones, and the forecast could reach many, many people. The while there's just a small number of people that have smartphones on the shore now, and most of them, well, excuse me, there are a small number of fishermen who have smartphones, and that's growing. But most of the fishermen, they don't want to bring the smartphones with them on the boats because they're expensive. They don't want to lose them. So that's an issue. But this is an example on the right here of how last year, this was after HIGHWAY was over, a forecaster in Uganda put out a nowcast, which is the text in the top image, and also attached the radar image to this text and sent it out. And of course, she's saying at this time, a line of thunderstorms over the lake. The storms are intensifying with strong winds. Postpone all trips to the lake. Be safe. And then later, she updates it 3 hours later, saying that rains will be clearing over zone 1 in the next hour. However, zone 2 is still having heavy rains. Zones 3 and 4 are safe. And so talking about going from nothing to very specific forecasts, this is a terrific tool. So from the social economic benefits of the HIGHWAY project, the impacts of these new marine forecasts include that many more people are wearing life jackets, boats are postponing trips after severe weather warnings, fewer people are drowning in the lake, there's fuel savings, fish dryers are cutting losses from the rainfall, and transporters are carrying lighter loads if warnings given. So the SEV study shows that in reality, there's maybe 1,000 deaths occurring per year over the lake, not as high as originally thought. And that due to these user-friendly forecasts and training, at least 312 deaths per year being avoided. That's terrific. And the overall project has a social economic benefit of $44 million in savings for this effort, and that's tremendous. So HIGHWAY was a really important, positive project that has occurred. These last few slides are, I'm not going to go through them in any detail, but they're here for you to go back and look at. And it's just to talk about the challenges, or you can view them as opportunities for not just Lake Victoria Basin, but other areas. And we know that with the advent of some new satellites, that it's going to be a tremendous boon, especially for the weather services in Africa, because all of a sudden now they're going to have high update rate imagery, 30-second total lightning data, and sounding information. And in particular, some of these products are going to be combined so that they can be very seamlessly included in National Weather Service prediction models and with radar. This is just an image, a loop, actually. Turn that off. From Steve Goodman et al., showing a week worth of lightning data. And again, having the lightning data on satellite means now it will be free to forecasters. They can see the evolution of the lightning and storms, and they could be tracking these lightning signatures and forecast, extrapolating them into the future for short-term nowcasts. Okay, so in the East Africa region, and Lake Victoria specifically, there's no direct water or near surface air measurements on the lake, no buoys on the lake. The marine forecasts underestimate wave heights on the open water. There's no capability to forecast water spouts, and there's no real protocol for producing nowcasts and warnings. But they do have a Vision 25 for the future, and that includes installing AWS on the islands in the lake, installing weather buoys, trying to install a new upper air station at Mwanza. and also installing a new radar near Kisumu, Kenya. And you can see in this image on the upper right here that if you have a radar that's installed there and you have all these other existing radars, you could produce a very nice mosaic over the lake, which would also be very high resolution data where you can look at the severe storm attributes of each, the severe attributes of each storm. This should definitely improve the accuracy of nowcasts, and it may help improve the detection of waterspouts. This is just what you need to be able to accurately nowcast high impact weather when using radar data. And I'm just going to step over this for now because I'm running out of time. But most important, you need full support for this type of an instrument to get really good quality observations to the forecasters. In Vision 25 too, one thing I didn't realize was going on is that each day forecasters from each country participated in the forecaster conference call to discuss what the severe weather was going to be or were they expected for over Lake Victoria. So that's pretty neat that they had already made that step. And in Vision 25, they hope to build on that and do it for the broader East African region. There needs to be improved wave forecasting modeling. There needs to be continued verification of the models. We need to get those upper air stations working again and a ready, constant supply of consumables so that radiosonde data is available. And we need to engage the WIGOS Center in Kenya to share data and the universities to participate in this continued effort. Okay, I promise these are my last two slides. What was used in the early warning system for HIGHWAY was essentially 6 to 24-hour forecasts, convective outlooks, watches, and advisories. And these allowed the fishermen and other people along the lake to take action to plan their daily activity. However, the early warning system were not really warnings in the traditional sense of how we use it, how WMO defines it, which is that it's an alert for impending severe weather where immediate action should be taken to save lives and property. So to provide the location and time-specific warnings that are required, you need frequent updated observations and nowcasts and warnings that get to the forecast office in a timely fashion, and improved methodologies for disseminating warnings to fishermen who are already on the lake and communities that live along the lake. And this is true not just for East Africa, but anywhere that you have a severe weather problem. Okay, and one last thing here is that currently no information gets to the fishermen once they're on the lake. They don't have their smartphones, and so they have no awareness of where the storms are occurring and where the high waves are. And so this is still to be solved. Okay, thank you.
Hi, Rita. Thank you very much. It was a very nice presentation. Always amazed at how much stuff you guys were able to do on this project. And so everyone that is online here or Google Meet or at YouTube, please post your questions on the chat. And to start questions, actually I wrote several here. I'll choose one. So it was an amazing project with a lot of tools and research for developing countries. Did you do or intend to do a follow-up on how the HIGHWAY project actually impacted the operational National Meteorological and Hydrological Services? Like, did they assimilate of any of the tools or the data or models in their day-to-day operations?
The only thing that we did within the confines of HIGHWAY funding was during our second virtual training of the forecasters. It wasn't just Uganda forecasters, but the forecasters were invited from the region. And we asked them, after doing the training and providing the online materials, to fill out a survey of, did they find the information useful? Would they use it in their forecast process? We got positive responses for that, but that's just a preliminary look at how they were mostly using radars and talking about nowcasting. I think that, I mentioned Ana Del Moral Mendez, and she's very interested to pursue following up with the forecasters in the forecast office, really have that communication and dialogue and see what's helping them, what tools are helping them, what could help them better. But that wasn't done under HIGHWAY.
Will it be done on the 2025 vision or something like that?
Yeah, I think hopefully maybe under the wiser African funding, she'll conduct that study.
Yeah, it would be very interesting to see.
Yeah.
So, Hernani.
Okay, I have my microphone muted. Okay, so thanks, Rita, for your presentation. Really very nice to see the result from the field campaign and the project. And it reminded me, I had some flashback from the Relampago campaign here 4 years ago. And yeah, I have one first question, which is more from a technical side. We see that there is a very complex terrain neighboring the lake. So is the radar operation there too much limited by ground clutter and beam blockade issues? How was your experience with that?
Yeah, they do have ground clutter issues. These are pretty nice radars. The EEC radar was in Mwanza, and the Vizsla radars in Entebbe. And they have clutter filtering routines. They just weren't optimized, I would say, for removing a lot of the clutter. If the Kenya Weather Service does procure a radar, they're going to have the larger issue because they want to center it where it's going to be over the water, but it will also be over the highlands too. So yeah, there are challenges with that for sure, and especially to see the daytime storms and how that's impacting the region.
All right. And I have a question by Rachel. Do you want to?
Yes, I have several here. What was the biggest challenge in terms of the background the forecasters needed? By background, I mean like a very broad range of things, like from physical knowledge and the interpretation of the data that you guys were providing them to technical skills. Did you guys have any challenge on that?
Yeah, I think there was a wide range because when I think of the radar engineer at Mwanza, he was very good, and he would contact the manufacturer if he needed any information. But he didn't necessarily know what he was really looking at, other than what storms are on a radar. And then there was a wide spectrum for the forecasters too. Some forecasters had no exposure to looking at radar data. And I also, you're probably asking me in a broader sense than just the radar. Some of these countries, I think it's only Uganda that was paying for the lightning data, the total lightning data. And the other countries wanted to have experience in seeing that data, experience in using the data too. But but there are always issues in getting data into your forecast office and displaying. And those were part of the challenges for the forecasters, is whether they could see some of this advanced information. And I think a lot of them couldn't.
So it would be like integration of the data in the end.
Yeah.
Visualization.
Yeah. And having it all centrally located for the forecaster, you know, a common display or a web-based system like you all have, or some way to see it all. Yeah.
Yeah, you think we have, but
Yeah.
we have, like, in research. That's what we are trying to do, the research to operations.
Yeah.
And side, it's usually what the meteorological offices do here. They have like several web pages, like, but the information is in different ones, and that's not ideal for nowcasting. So
Yeah.
And Nani.
Okay, all right. Well, I have a question more regarding communication, severe weather dissemination, communication. Are the severe weather warnings broadcasted for the general public, the true end user in English? Is most of the local population native English speakers, or are there warnings in different languages? And additionally, what means of communication are employed to disseminate these warnings?
Yeah, they definitely translate in English, but primarily in Swahili. But some of, like, I think Uganda has several dialects, and I think it's up to the broadcaster to decide, you know, in how many languages is he really gonna, like, transmit. But for sure, Swahili and English is transmitted. Yeah,
that's kind of an interesting challenge if you're in a place where there are so many dialects, and how to disseminate the warning. And yeah, that's something that I was just thinking about. And also, and regarding the means of communication, I mean, by radio, SMS, how usually this was performed?
Well, so not all radio stations broadcast. They didn't want to participate, but there was enough in each country of major radio stations and smaller ones that the word was getting out, and it was good. The SMS, it costs, right? You have to pay for that. And so the advantage of using the WhatsApp was more attractive, I think, to a lot of people because it's free. Well, the cell phone isn't free, but the WhatsApp is free. And yeah, I think that was how they tried to best deal with getting the word out.
And how was the cell phone coverage there? Like inside of the lake, like the middle of the lake, do they have cell phone coverage?
You know, I don't really know the answer to that. I just know I mean, okay, so Jim Wilson and I are out there, and we're trying to convince them to, you know, do these nowcasts and all, but we're being told that no, the fishermen don't want to bring any phones, or just a very basic one if they have an emergency. And I don't really know if they have coverage because it never gets that far, the discussion. I
think if it's the very basic one, it could have like actually like longer range coverage.
Well, you know, they do have islands in the lake. A lot of people live on the island, especially in the northern part of the lake. So, and they are using the WhatsApp. So there's some coverage of some sort for sure.
Yeah, maybe not whole lake, but
right.
Like not a whole ocean or satellite. Some of people use satellite. Yeah.
I did have a question for both of you or anybody that's on. It wasn't totally clear to me what you have available from the GOES. Are you getting any of the GOES 18 products?
Not A16 actually, but yes.
16, yeah.
Yeah, goes the first one. The first goes is 16 that covers here. Everything we get. So everything is either you can get it by the direct to broadcast when you buy the antenna and everything, and that is kind of expensive. So, but so we have just a few offices that have the antenna, and the other form is through Nowcast, which is a small antenna that was like huge effort to spread. Nowcast. So on that, the people get the offices get a few products and more downsized the data, and already worked on the data for a few products. And also, but the raw data you can get from Amazon Web Services or Azure and all those cloud platforms. But yeah,
so would you say that the lightning data is being used really efficiently then in the forecast offices along with the satellite imagery?
Not much. Usually it's a funny thing. What I see here is that they use the ground-based network lightning data instead of GLM. It is funny. It's very funny. It depends on the purpose, what you need lighting for. But usually, and another thing is that we have like 16 channels from ABI, and mostly they use the same ones as the old GOES 13, visible and the infrared. Don't use the other channels in other facilities. So there has been some efforts from NOAA here to do training on that, but still a little incipient. That maybe with we are trying to write out guidelines for nowcasting, so maybe that will help a bit.
Thanks.
Yeah, we do have a question by Rakesh Ghosh. I hope I pronounced correctly your name. Thanks for the question. Can you comment on the formation of nocturnal thunderstorms over the lake region? Is this related to elevated convection, whether it is difficult for the forecaster to forecast?
Yeah, so I would say that the large majority of thunderstorms that we saw, nocturnal thunderstorms over the lake, did initiate either on that northeast coastline or the north coastline. And then as these storms produce gust fronts, organized gust fronts, as they become organized into squall lines that produce gust fronts, those gust fronts move across the lake and trigger more convection. That doesn't mean that there couldn't be elevated convection occurring. It's just, I would say we haven't looked, because we are relying on one radar to cover the whole lake, and so we had to use the low PRF scan. We don't see all the surface or the mid-level processes going on in the lake further away it gets from the radar. So it's kind of a not a great clear answer, except that we know that a lot of the convection is boundary layer forced, whether it's a land breeze or a lake breeze on the shore. And I can't totally say how much elevated convection plays a role. But there's no soundings either right near the lake, and that makes it a little difficult to address that.
All right. Related to this, in this same context, one question I have is, what are the most common modes or organization of the convection? Is it like more pulse-type, short-lived cells, or do you have mesoscale convective systems based on your experience during the project?
So, let's see. This is a great question for Anna, because Anna has done exactly this kind of research. But I'm just going to represent very simply that there are isolated, there's a range. There's isolated cells, there's clusters of cells that just stay clusters, they don't organize. There are others that do organize, merge, either become linear features or maybe a little bit broader. She's gone through and classified all of those types of convection and determining based on the growth of the lines what type of upscale growth there is. I mean, you can certainly call some of these MCSs, especially when they're like squall line oriented and have a lot of precipitation, but they don't always have some of that same structure. I mean, it's a good sized lake, but it's not like Relampigo, you know.
There is a recent paper on Lake Victoria too, on how like they were trying to measure, I think, the lake breeze and how the convection triggered from that. I cannot recall the author's name, but it's recent, like this year or last year.
Yeah, I mean, there's a couple. I'm not sure which ones you're thinking of, but there have been certainly there was a lot of study on that, on the lake breeze, because you can see it in the daytime. You can see the cumulus clouds forming along the coast, and so I'm not sure which paper you'd be referring to, but there are a few. If you think there's one that just came out, maybe I should look.
Not sure. It's always like a mess. We see a lot of papers every day, so it's always a blur on my mind. So we have another question from Finber Frank. He says, great presentation. And would you recommend weather forecasts moving towards more images like icons and less words? Do pictures tell 1,000 words in Math 2?
You know, I liked the forecast that was produced for this. And I have seen on the WhatsApp that they'll send the actual icon graphic forecast out. Not often, but it is sent out. And I just think it's a great tool for a lot of people who just don't want to have to know how meteorology works or understand, you know, that thunderstorm 20 kilometers away may produce a wind that's going to affect me at my boat, you know. So I think there's really a lot of value in it, but you know, there are a lot of smart people everywhere that like to actually know the values too. I think you still need both. You still need to have access to both. But you know, even on our web pages, when we go to a particular city in the U.S., we see little icons. We see the sun come out and, you know, rain, and then, you know, so we're using them here too. They're effective for a quick look too. So what else did he ask? Let's see.
No, it's the same. It's just that. Yeah, I also like the combination of both, because like for what we see here in Brazil, when we say like it will rain like 35 millimeters, they have no idea what 35 millimeters is. They just, if you see the numbers a lot, maybe you get a sense that it is okay. It is too much for somewhere, but it's not too much for another place. And it is a social study, very interesting. So we have another question from Bruno Bainey. He's making a comment first. I really liked the way the forecast was produced to meet the needs and expectations of the users. As an operational meteorologist, this is a goal to pursue. Now a question. He says that he lived just for a little bit, so maybe it was already answered. How was the process to develop the new forecasts? Was it like co-working process, forecasters to users?
No, yeah, it was a co-design process, and they based it on other, I mean, the UK ran it and facilitated these workshops with the spectrum of stakeholders and users, and they came in those workshops together to say, this is fishermen saying, this is what we need. This is what I understand. I understand wave heights and relative to my body. And so I thought that was really excellent. You know, they got all the players together, they talked, they convinced the director generals of each weather service to go through and try this out, and they bought it and they made it happen. And so that's the big success, I think, is that they all work together, and that doesn't happen a lot, right? It's hard to you're so busy trying to produce your good forecast or nowcast, maybe you don't have time or funding to go work with your end user to get what they really need.
All right. I think we have asked all questions here. I do have one last question from me, which is there any plan for or future plans for other similar projects in the area, or something that you or someone that you know who participated, who is envisioning possible continuation on this type of project in the area? Yeah,
so as I mentioned a little earlier, WISER, which is an acronym for, you know, it's the umbrella of funding for Africa, and particularly East Africa. It's put out a call for proposals for work in that region. As I mentioned, Anna and also Tammy Wentworth have submitted a proposal to carry on, to go to the next step, especially in the nowcasting realm, and address their social concerns in producing nowcasts, you know, what they have to do in the forecast office. But like Kenya has already been awarded funding through the WISER program as well. And then there's other programs like World Bank. I don't know what they're doing, but African National Bank, there are funding pots, and that's the only way things seem to happen.
Perfect. Yeah.
Yeah.
And out of curiosity, do like those countries have universities with meteorology program there, or they get meteorologists like other, like, I don't know, defense or?
Yeah, that's the kind of the missing player, I think, in this whole thing is, and it's important to engage them more. I believe my understanding for most of the universities is they may have a physics major, and so those who do the physics major then often go out of the country to get further degrees. But those that are the meteorologists or meteorologist technicians, they come into the Weather Service and get trained in the meteorology, and they're trained by forecasters and managers in the office. So that's my understanding of the process. And so I don't know that they specifically have any meteorological degrees offered in the universities. So.
Yeah, okay. No, I asked it because we, like in the past, had a few programs with African countries, but it was like Portuguese-speaking African countries that they would come to our graduate program to get their degree. It is a very nice interaction. We always liked to have them here.
Yeah, I think that's fairly common for sure to do that.
All right. I think that with that, we addressed all questions and comments, and I really thank for everyone who placed questions in the chats. And I don't know, Rachel, do you have any additional comments or question?
No.
Okay.
Just that stay tuned for the next.
Yeah, and we would like to thank Rita for the great talk. It was really nice, and as we mentioned earlier, this was recorded and will be made available in the YouTube channel of the Department of Atmospheric Sciences of the University of São Paulo. And so again, I'd like to thank Rita for the great talk.
Thank you.
Thank you very much, Rita.
Thank you. Bye-bye.
Okay.
Bye-bye, everyone.
Bye-bye.
Have a great rest of the day.